Creep. Creep is a mechanical property of materials characterized by time-dependent, slow, and progressive plastic deformation under constant stress or load, typically at elevated temperatures, often above 0.4 times the material's absolute melting point. It occurs even when the applied stress is below the yield strength. Creep is a mechanical property of materials characterized by time-dependent, slow, and progressive plastic deformation under constant stress or load, typically at elevated temperatures, often above 0.4 times the material's absolute melting point. It occurs even when the applied stress is below the yield strength, involving mechanisms like dislocation glide, diffusion, and grain boundary sliding. Creep is divided into three stages: primary, decreasing strain rate; secondary, steady-state strain rate; and tertiary, accelerating strain rate leading to failure. Creep is critically significant in engineering design for components operating under sustained loads at high temperatures, as it can lead to dimensional changes, loss of functionality, or catastrophic failure over time. Ignoring creep can result in over-design, wasting materials, or under-design, safety risks. Its study helps in selecting creep-resistant materials like superalloys or ceramics, and in predicting service life using models like the Norton-Bailey equation or Larson-Miller parameter. Numerous examples illustrate creep's importance. In gas turbine engines, for example jet engines, turbine blades experience creep due to high centrifugal forces and temperatures exceeding 1,000 degrees Celsius, leading to blade elongation that could cause rubbing against the casing if not accounted for. Materials like nickel-based superalloys are used to mitigate this. Steam turbine components in power plants, such as rotors and casings, undergo creep from constant steam pressure at 500 to 600 degrees Celsius, potentially causing warping or rupture after years of operation, which is why creep testing, for example via ASTM E139, is mandatory for longevity predictions. Nuclear reactor pressure vessels and fuel cladding creep under irradiation and heat, affecting reactor safety. For instance, zirconium alloys in reactors can deform, leading to fuel rod bowing and potential coolant flow issues. High-temperature piping in chemical plants, for example refineries, carrying hot fluids can sag or burst due to creep, as seen in historical incidents like the 1989 Exxon refinery explosion, partly attributed to creep-weakened pipes. Aerospace structures like rocket nozzles creep under thermal loads during launch, influencing thrust vectoring. NASA's use of refractory metals in nozzles prevents excessive deformation. Bolts in high-temperature flanges, for example in boilers, can relax due to creep, loosening connections and causing leaks. This is a common issue in fossil fuel power stations. Incandescent light bulb filaments, tungsten, historically failed from creep-induced sagging,